Alright guys, I have another video about conservation of power and just one of the applications to it. This one kind of seems a little bit odd for folks when we first introduce these concepts, but I'm just going to start off on this video by saying up front, this is not hard at all. It's just basically reverse engineering a system and knowing how much power is actually being supplied into the system with basically just little bits of info. And lots of the time we talk about power factor being lean or lagging. Sometimes we talk about just knowing about the apparent power. Sometimes we talk about the real power or just even reactive power. But with a combination of just a couple of these, we can actually go through and just re-engineer basically, go back and figure out everything that we need to know about the system with just a little bit of information. So to start off with these concepts, let's actually go back to just some base definitions. And if we know the base definitions and equations for basically real power, even reactive power, or even just complex power, then we can actually take some of this information and just find out what we need to know about everything that's actually being supplied to each load within the system. So let's take a look here. Now, complex power, at the very beginning, we've been talking about this consistently, where complex power S is made up of P plus JQ, and it's actually plus or minus JQ, depending upon whether the system is more inductive or more reactive. But here, real power with our imaginary power, which is our reactive power, and that's the rectangular form. When we convert that into basically its polar form, we get basically the magnitude, which is that apparent power. Remember the magnitude of the polar form is actually the apparent power. And even though we obviously know it's S at an angle of theta, and that's theta V minus theta I, then I just went ahead and put the brackets over it just to once again stress the apparent power portion of that. But we know that the real power is equal to the apparent power multiplied by cosine theta. And for the reactive power, that's nothing more than S, or the apparent power multiplied by sine theta. And obviously, if we know that theta itself, theta is basically that phase angle that's between basically the voltage and current, theta V minus theta I. So if we know that, then we can actually say something also about the power factor itself, because we know that the power factor was equal to cosine of theta V minus theta I, or just cosine, in this case up here, of theta. And in this case, guys, if we have the power factor, if we take the inverse cosine of that power factor, we actually have theta. And knowing that also that power factor is also the real power over the apparent power, and if we know that power factor is lean or lagging, then we automatically know whether the system is actually going to be mostly inductive or even mostly capacitive. So we could start off actually having just little bits of information here. We could actually have basically our power factor and the real power, and we could actually kind of reverse engineer everything so that we could actually know what basically Q is, or the reactive power. So a typical question that we would have in a situation like this is we have two loads, and in this case I have two loads and a source. And the first load, S1, basically says that the apparent power is just 100 volt amperes with a power factor of 0.8 leading. And when we say 0.8 leading, obviously that just means that it's going to be mostly negative reactive power or capacitive reactive power. And over here on the second load we have P, and that's equal to 500 watts with a power factor of 0.75 lagging, which means that's mostly inductive. So a question that can be typically asked in this type of scenario is, what's the total power total complex power that's actually being supplied by that source? And if we look up here, well, how can we actually determine that? If we have the apparent power, we have the power factor, but we have the real power over here, but we don't have the reactive power. How can we actually go through and determine what power is actually being supplied within the system? Well, a couple of things. We know exactly by these definitions that some of this information may help us go back and rederive the extra information that we actually need in the system. And if we're looking at two independent loads, then we know that the summation of the real powers and the summation of the reactive powers by the law of conservation of power would actually give us everything that we need to know in the system to derive basically the total power within the system. We're going to come back to this over here to answer the question, but we can see up front that if we had the real power of our first load and the real power of our second load, we could add those two together to find the total real power within the system. Or we actually can conversely just go through and add together their reactive powers, whether they're inductive or capacitive. And that gives us so much information that we, in the appropriate amount, that we basically just add those two complex powers together to rectangular forms. We add the real portions together, add the imaginary portions together, and then we have everything that we need to know in order to derive the total complex power that's actually being supplied by that source. And once again, this is another application of the law of conservation of power that says all the individual powers that are being delivered to each load, if we just add those up, that is the total power that's being supplied by the source. So let's see here. Let's see if we can actually go through and derive the information that we need to know about each load here and the total power that's been delivered to each load by these little bits of information that we have. So first off, we know that the power factor is equal to 0.8 leading. So we can easily just take the inverse cosine of that and get 36.87. And if we have that phase angle, then if we also have the apparent power, then by the notion that P is equal to the apparent power multiplied by cosine theta, and that the reactive power excuse me guys, is equal to the apparent power times sine theta, we can easily go through and find the real and reactive power. So the apparent power, 100 volt amperes, multiplied by cosine 36.87 gives us 80 watts. For the reactive power, 100 times sine of 36.87 degrees, that gives us 60 var. But we know that this says power factor of 0.8 leading. The power factor of 0.8 leading means that we're going to have a capacitive system, because that means that the current leads the voltage, and that is capacitive. So we know that capacitive systems have a negative reactive power. So all we have to do to know the rectangular form of the complex power is just say, oh, 80 minus 60 volt minus J 60 volt amperes. And if we convert that into its polar form, sure enough, all we have right here is 100 and angle, oh, there it is, negative 36.87. Now, there's two different ways that you can actually solve for this. We could easily just, at the very beginning, all we had to do was say, well, we know that it's going to be leading. This is actually going to be for the purpose of this discussion. For the polar form, we know that would actually be negative 36.87 degrees. We take that 100 volt amperes, there's our polar form. And all we have to do is convert it into its rectangular, and we would actually appropriately come out with P and Q. The reason why I did not put the negative sign right in here is because we take that negative sign into consideration when we actually get down to putting P minus JQ together. Alright, so this one's very, very straightforward. We had the apparent power and we could get our phase angle. We, by definition, can easily just go through these three forms right here and just quickly find exactly what we want in terms of the real power and reactive power of the system. Let's take a look over here at the second one. Now this one's a little bit different because we're going to be kind of working backwards with what we have. So here we just have the real power. Real power is just 500 watts. The power factor is 0.75 lagging. So we know it's going to be inductive in nature, so it's going to be P plus JQ, not P minus JQ like we had down here in our first load. Let's take a look here, guys. So in this instance, here we got basically power factor of 0.7 lagging. We take the inverse cosine of that, bam, 41.41 degrees. So here we know for a fact that if we have the real power is equal to the apparent power multiplied by cosine theta. in order for us to actually get the reactive power within the system, we have to have that apparent power first. The nice thing is because we already know that that real power is equal to the apparent power by cosine theta, we have theta, we have the real power. All we have to do is just a little bit of algebra and basically divide through by basically cosine theta, and that will actually give us our apparent power when we divide cosine theta into basically that real power. We know guys, that the power factor already tells us basically P over the apparent power. So that ratio, that's really what cosine theta V minus theta I gives us, is the ratio of real power with that apparent power. So all we have to do here to find S is, once again, divide the real power, 500 watts, divide by cosine theta, or 0.75, and then we actually get 667 volt amperes. Piece of cake. Now we have our apparent power, 667 volt amperes. So in order to find the reactive power, boom, here we go. Q is equal to the apparent power times sine theta, 667 times sine of 41.41, and that gives us 441 var. So the total complex power in our second load, S2, is 500 plus J441 volt amperes, or 667 at an angle of 41.41 degrees volt amperes. And so guys, to answer the question on this problem, all we have to do is come up and actually just take these two right here, what we found for the complex power, and just like we said before, we just add them together. We just take those two, add them together, and that is 100% the power that's being supplied by that source. Let's take a look right here. P1 plus P2 plus J Q1 plus Q2, so we got 80 watts plus 500 watts, plus J negative 60 var plus 441 var. And so the total that we get here is basically 580 plus J 381 volt amperes, or 726.6 at an angle of 37.25 degrees volt amperes. But guys, do we have an efficient system? Is it efficient? And we can obviously look down here and looking at that phase angle, looking at that reactive power to the real power, it's not efficient. Got a power factor, that ratio is 0.8 lagging. That is not what we want as an efficient system. We could easily just come through here and decide that we want to bring that down by a certain amount of reactive power and then derive a capacitor. We could pop that on to the end of this thing if we want. You guys could do that because you guys have been doing that up until this point. But for a problem like this on the test, for our final test in this class, we're probably going to come back and you're going to see a problem very, very similar to this, where you're just going to have to go through with a little bit of the information and just kind of rederive it. But the nice thing is, guys, is that all we have to do to rederive it, everything we need to know, going right back to the beginning of our discussion about power within this section of the class. All right. So from here, we're going to continue working with three-phase power, but I want to make sure backtrack just a little bit so that we go through and make sure we've covered this portion, and that really completes our discussion of basically the conservation of power. All right, see you guys on Wednesday.